Hi there, my name is Emeka with SkyCiv, and today we're going to be talking about fixity codes and how to define them for various different member ends and support connections in our software. We're going to be going over just kind of a general introduction of how we define fixity codes with our software. I'm going to talk about the different kinds of members and how those relate to different fixity codes. And then we'll give a couple examples of how to define different fixity codes in our supports and at the member end. And lastly, just kind of give some other information on various different types of supports. I'm going to be following along with this tutorial that we have here, which you guys should be able to follow as well. And we also have some links at the bottom of this page that give some additional resources that you can look at as well. So first of all, I'm going to open up a new structural 3D program. And we'll just start with a new one. And so the first thing I'm going to do is talk a little bit about, what fixity codes are and how we use them, how we define them. So the best thing to learn is that for our fixity codes, we tend to use 6 different letters. The first term is going to define the x-axis, the second term y-axis, third term the z-axis, and then for the fourth, fifth, and sixth, we follow that same convention. So it's x, y, z, x, y, z. The first 3 terms are talking about translation. So you can think of them about how a member is going to slide in 3D space. And the last 3 terms are talking about rotation, and it's determining how the member is going to rotate in 3D space. So essentially what we tell when we define a fixity code, we're essentially saying at this specific node, the member, how can it slide in the X, Y, and Z direction, and how can it rotate in the X, Y, and Z direction. So the thing you can know is that for SkyCiv, let's just draw a quick member here. I'm going to define, just have one node 0, 0, 0, and we'll just have one at 1, 1. If I draw a member between those two, now we have this member here, and it's going between nodes 1 and node 2. So if I don't have any supports right now, this member is just kind of floating in space. So if I was to try to go and solve the program, it's going to give me that error. So what we'll do is go and set a support. Let's put a support at node 1. So now we've told the software, hey, this thing is fixed at node 1, and then node 2 is free to rotate. So this could, maybe be like a cantilevered beam. This could maybe be just like a column, like a freestanding column that's fixed into the ground. But there's no way for the program to really know how this bottom part is restrained without us defining it. So say, for instance, we want this to be a column. Let me make sure to use the y-axis vertically. So if I wanted to shift node 2 and say we're defining this as a column, the x would still be 0, but we'd want in the y-axis this to be going up, right? So now we have a column here. But there's no difference between this to our program right now and this, it being like a cantilever beam, because we haven't defined, what the support conditions are going to look like. So if we go back to this being a column, I can think, okay, if this is a freestanding column, I don't want it to slide in the X, Y, or Z direction, right? But then when it comes to rotations, we don't even want it to rotate about the X, Y, or Z direction either. So the best thing for us to do is we go back to our support here, and under the restraint code, you can see right now it's all 6 Fs. That one's good. So basically it's just being able to say, hey, in the X, Y, and Z direction, I don't want this to be able to move at all. I don't want it to rotate at all. Just be fixed in all directions. Say we had a different condition where let's try to do a cantilevered beam now, or like let's do a simply supported beam. So I'm going to change the nodes for 2. As we're going to do a simply supported beam, let's just have it starting here. We'll go maybe like 10 feet out or 1 foot out. So we go back to 0. Let's just go 1 foot out in the Z direction. So how it's defined right now, we basically have it fixed here at node 1. And then at node 2, there's nothing there. So this is essentially just a cantilever beam if there was a wall here. If I wanted to change this and say, hey, I want it to be a simply supported beam, then I might have a support here. I'm going to have to also add a support here at node 2. But let's make the support at node 2 just like a roller. And then we're going to have support at node 1. I don't want this to be fixed. I'm going to change this to a pin support. And so if I click on this, we can see now, okay, it's fixed in all directions, but right now it's allowing it to rotate about the z-axis. When I look at my model, so right now this is having it rotate about the z-axis. I don't think that's right, because basically what I want to have is a simply supported beam. is for the beam to be fixed in the X, Y, and Z direction in terms of translation. I don't want it to rotate this way about the Z axis, and I don't want it to rotate about the Y axis. What we actually want is it to be able to rotate about the X axis. And so I'm going to have to change this restraint code to RFF. Hit apply. And then for this one here, this roller support, if we think about it, we don't want it to rotate. Actually, we want it to be free to rotate pretty much in all directions because there's not going to be any, fixity for it in terms of rotation. But we don't want it to be sliding in the X direction. We don't want it to be sliding, say, in the Y direction. We want it to be released to be going in this direction. And so that direction is Z. So what we're going to actually change here, let's go back. We're going to have FF released in the Z direction and hit apply. And so right there, that's how we would define a simply supported beam using those fixity codes. So I've kind of showed you guys how to do that with regards to, the ends of supports here, like if we're defining these restraint codes. But the other thing that you can do is if we're actually creating, say, like a frame, like a moment frame, we'd want to define how these fixities operate in relation to other beams. So let's just start from scratch. And let's just draw a quick moment frame. So I'm going to have one at 0, 0, 0. We're going to go up, say, 5. I'm going to stay at 5. I'm going to go over 5. And then we're going to come back down, so we'll keep it at 5. So we're basically kind of drawing a moment frame this way. And so for the members, we're going to define it going from 1 to 2. We're going to define one from 2 to 3. And then one from 3 to 4. So we've kind of created this moment frame here. And so similarly to what we were talking about before, let me just double check, make sure this is right. So the vertical axis, yep, is in the Y. So how we were defined it before, we're going to have to determine how these supports are going to operate. So for this particular moment frame, let's just have we're going to have at point 1 and point 4 fixed. So we're going to go back to the supports. And like we did it just before, point 1, we'll have it just a fixed. And then at node 4, we'll have it fixed again. And so like we were saying before, FF again. So basically fixed in all translation, fixed in all rotation. So when it comes now to these individual members though, you can see that we have node fixities for node A and node B. So node A is starting at this point right here. Node B is up here. If we look at this one right here, node A starts at node 2, node B is node 3, and we have these fixity codes here. Those are currently grayed out because what we have right here is we've selected that this member is a frame member, and that's just what it is defined as default. So what we've kind of discussed here and we've shown is that you have different types of members. So you have like your frame members, you have your truss members, and these are just basically talking about your different kinds of members. You can read more about them here in this article. But the thing to keep in mind is just that when we have frame members, the idea is that they're going to be under a lot of axial load. And so we want the joints to be fixed at each point. We want it to be kind of rigid. So you can think of this as like, say, like a moment frame, right? We want all the moments to be transferred. We don't want it to be released anywhere. When it comes to like truss members, though, you can think of this as like, say, like a steel truss or a wood truss. We want those connections pinned so that the member can actually like release any kind of internal moments that are created, but we want them to actually transfer on. We basically, while the truss members transfer axial loads, we don't want them to transfer any shear moment forces. So you can think of it like having those pin connections allows us to transfer those loads. So when we look at this model here, as we've defined it, I'm going to just apply. So as we can see here and here, all these are just all the way fixed, So if I was to go, let's just add some self-weight. Apply. I'm just going to add some basic load combinations. If I was to solve Yeah, let's give it a basic section as well. So we could see here, this is just like the typical reactions you'd expect from like a moment frame. So it's coming here. This is kind of neutral point, comes here. We're seeing just some bending here and then bending there. If you want to actually see the actual displacement, you can see how it's under stress. So the weight's coming down from here, slightly buckling here, but you can see since this is fixed, there's no, this point and these points are fixed. So there's actually keeping them in place there. So if I was to go back to the model, right, and say we were creating, let's say if one of these was released, this might make the project unstable, but let's just say this was a pin connection instead. We go back to solving it. Let's go to this placement. You can see now this part's remaining fixed, but now it's transferring the loads because this is allowing it to actually rotate due to the moment that's being introduced from the self weight. It's actually bowing out this way, and we're not seeing, that second order kind of reaction that we're seeing actually here in this one. So that's kind of how you would start, playing with the different kind of end conditions, and why it's really important to understand what the specific conditions of each endpoint you're using are, because if these are not fixed or these are released or whatever it might be, it's going to impact the analysis, and that also is going to impact the displacement, and that's going to impact the axial and moment forces that are being translated throughout the structure. And then just one last thing. So if we switch this back to fixed, let's say, and for these members, let's say we want to do a custom and we want to define it. Let's say I want to release the moments for a point at node 2. So we see node A, instead of having this be like a moment frame, let's say these are all released. And I actually want to actually do the same thing at node 3. And so this is going to be similar slightly to almost like a truss element, at least at these nodes, in that the moment forces are going to be transferred out. So if I go here and solve again, you can see how there's, this moment's not really, it's the moment force that we're seeing here is not being transferred down to these members, because since this is released here, the self weight comes down, it's stressing this member by itself, but it's not being transferred into any of the other members as well. So those are the main things to think about when you're thinking about the member end fixities, as well as the different types of supports. But one thing to keep in mind is that, you might have certain other conditions, whether it's, you have like a slider situation where if there's like a slot that it's able to move, you can think about it in that case, whatever direction, whether it's the X, Y, or Z that you're allowed to be released. We're basically saying, hey, in this case, this member is allowed to move and translate along the X axis and then rotate about the Z axis. So that would look like in our model, if the member was able to slide along here, but then rotate about this axis here. And so another case we might have is, say we have like a hinge connection where, again, this is locked in, so it actually can't slide in any direction. So X, Y, and Z, you see those are all fixed. But then what we do have here is, instead of it just being like welded shut, we've switched this one to being released in one direction. So you can think of that similarly how we had maybe, say, this pin connection here. If we go back to supports, this pin connection here, it was released in all the different directions, but then in that one direction that we wanted to rotate around, it's released. And so again, this is just how you can begin to modify your own structures to be able to ensure that they align with just the different fixity conditions that you're trying to introduce. And so just to kind of close out this project, there are kind of three main, when it comes to supports, types of supports you're going to see. You're going to have like a fixed support, which is like we were mentioning with that moment frame, where where it cannot rotate it and it cannot move in any direction. You might have the pin support, where it's going to be released in one specific direction. And then kind of similar to when we were showing that simply supported beam, you might have a roller support, where it's not allowed to like translate in certain directions. But again, we want it to be able to roll back and forth and translate in one direction. And so the one other thing that I'd like to maybe point your attention to, and something that some people might find interesting, is when it comes to spring supports. I know we have some users sometimes that will ask about that, and so we can read more about this in this link I've added here. But you can also always introduce spring supports, and so that you might have to define in specific conditions. Like let's see if I go back to that simply supported beam that we had earlier. Node, we'll put 0, 0, 0, and then we'll just draw one at 10. And then we'll draw a quick member. 1, 2, apply. And then what I'm going to do is I'm going to add at point 1, just a simple fixed support. And at node 2, what we'll actually introduce is going to be a spring. But what I want to do is I'm going to have a spring support here that's going to be depressing it in the vertical Y direction. So let's do, 2. And so the one thing you're going to have to figure out is what that, the K coefficient is, like the stiffness coefficient. For this specific condition, let's just pretend it's 1 kilonewton per meter. Hit apply. So now we have a spring here. And so if you can think of it now, like when this is being depressed, this point is going to release some of that moment condition. So the moments are not going to translate because this is a pin connection, but there should be somewhat of a vertical force coming down on this spring. And so if I was to go, again, let me go to self-weight, make sure that's on, make sure my section's still defined. And we'll just use some basic I-beam and submit. So now when I go to solve it, if we look at this placement, so you can see here it's being depressed here, and because of just the weight, when it comes to this point right here, it's still fixed, so it can't actually translate. But if I was to go to the 3D, you see it's being pushed down here, and we can actually see the resultant load based off of this spring member. So let's go to solve, report, nodal results. We'll create a report. See that report, and we're going to go to that specific node. So we see node 1. So we have a reaction at node 1. We don't have any reaction at node 2 right now. So we see the force that's coming down in the Y direction, and that's what's being pushed back. So again, you can play with this. I know some other users, what they sometimes will do when it comes to spring supports, you might have, say, a plate, and we'll just define 0, 0, 0, 0, 0, 1, 1, 1, 1, then 0, 0, 1, 1, 0, 0. Create a plate, 1, 2, 3, 4. So we've kind of created a plate here. And say this was a footing, and we wanted to have the footing being depressed down on. Having fixed supports at each corner is not going to really replicate what we're trying to do there. So if I was to go, though, and go, let's mesh this plate. So before I do that, let me just go to supports. If you go here, add a surface spring support. We have the bone ID 1. Again, now we're going to have to add the modulus of subgrade reaction. This you'll probably get from your soils report. Let's just give it a 10. And we're going to have this be compression only. Good views. server spring support, plate ID 1, 10, submit. Okay, let's try this one more time. I wanted to create a support, add server spring support, plate 1. There we go. So let me remove these node labels, and we'll go with the plate mesh nodes, the plates. And so what you're seeing here, if I was to zoom in, is you have a bunch of minor springs that are replicating that soil surface condition. So you can imagine as we're pressing down on the soil, the modulus is basically creating like some kind of a compressive force on the soil that's being pushed back up. And that's what this load is replicating. One thing to keep in mind, and we usually tell users, is, because if I was to analyze this right now, I'm probably going to get an error saying that this is unstable. What you want to do is actually pick one of these spring nodes, because right now this is unrestrained. So just pick one of these spring nodes, switch it to a fixed support, and then you should be able to solve with your model. And that's probably the most often used case of spring supports. You can obviously do it in other conditions, other situations, but this tends to be the most often situation where it's being used. But again, that's kind of a general overview of just fixity codes, how they relate to SkyCiv, specifically in structural 3D, and how you use them to define the kind of fixity conditions at the end of members, as well as supports. Like I mentioned before, this is kind of a good general overview. We have a lot of different articles that talk about how to model, say, a hinge, the difference between truss and frame members, and then also specific to when you're looking at spring supports, we have a lot of more information. You can follow that here. But this should hopefully give you a good understanding of how to get started. And after watching this, hopefully you have a better idea of how to use fixity codes and how they can support your design. So thanks for watching and have a great day.